Okay, welcome everyone. We would study the basics of matrix algebra, and we'd only learn the things that are extremely needed for understanding complex uh, structures within or complex calculations within uh, machine learning and spatially optimization. So the first thing that we would learn is very simple gradients. Now, there are two building blocks of anything that has anything to do with machine learning. One is, of course, vector, which is just an array of numbers. And then we have matrix, which is nothing but a 2D structure where we have rows and columns. Now, we generally write the vectors and matrices by mentioning their dimension. So for example, if Z is a vector, then we write something like Z belongs to R to the power M, denoting an M dimensional vector, which basically nothing but a list of M elements. And similarly, we can write something as R to the power M cross N if this is basically a matrix of dimension M cross N. Now, one must understand that one possible uh, option for writing this such a matrix as M cross N is because it's can take something of dimension M and can output something of dimension N or vice versa, depending on how we want to write down the matrix. But here we are more interested on functions of vectors and functions of matrices. So you can assume that we have G of Z, which is nothing but um, a variable that can be mapped to another value. So let's deal with in the realm of real numbers. So Gz becomes a real valued function, which basically takes an m-dimensional vector and gives us a number. So you can think about G as anything. You can assume that it probably takes a vector of some properties of a house. So, for example, a house has area, and it has a location parameter, and it has an age, and then it can predict a number which is a real valued number, maybe price. In that case, such a function will be a real valued function which takes a vector and gives us a real number. So this is one very solid example of real valued functions. In the similar fashion, a function can also, maybe I should write a different term to denote a function that can, take a multidimensional thing, which means that maybe again an m-valued vector and also gives out another vector. And you understand that why I came to this function, because this is again a vector valued function. So in general, when we write vectors, one of the assumptions that some of the writers take is that those are regarded as column vectors if nothing is specified, which means the vector is like this, or versus the row vector. So when I say that I have a function which is a real valued function, then this is one of the ways to look at it. Now, you might ask that, okay, what would be an example where a function takes a vector and then gives out another vector? Now, this also happens quite a lot, actually, even more than what we think. For example, you can assume that you have a multidimensional data set, which means that you have data where each of the data set have many, many features. For example, you can imagine uh, a sentence. So, a sentence can have many words, which means that each word can be a feature. So you have, say, sentence one, which have multiple values, and each of those values could be a token or a word. And you have another sentence, which again is a bunch of tokens, which could be assumed as values. And then you can assume that you have a function, say h, which takes each of these sentences and then convert them to a point which have two dimensions, x and y. Now, this might seem like an example which might not have a very real meaning, but it is extremely interesting, as you would see, that this would give us a power to cluster sentences which otherwise can be uh, objects which are hard to quantify. So, for example, if you have sentences from a physics book and you have another set of sentences which comes from a history book, then when you map these sentences into 2D points, you might see two clusters, at least that is expected, in which case you are actually mapping, say, your vocab size or your token sizes, I don't know, or number of words in sentences, probably 100. You are mapping that to a two-dimensional object. Now, one thing to remember that all these examples I have taken, I've consciously made a choice to only take real values. Now, this doesn't necessarily mean that we will always have real values. We can have anything, but just, to mention that, okay, it means that real valued functions are mostly usable and understandable. Okay, enough about vectors and functions of vectors and matrices. So we actually introduced a few things which it's easy to just write them. So for example, we have assumed that we have a vector quantity of dimension m, which I mentioned before that it's a column vector to specify more. Then we have a function uh, g and h, actually two functions. One function is a function that takes a vector and gives us a real number. And then we have a different kind of function which takes a vector and gives us another vector of different dimension. And we have seen two different examples where these functions can be useful. Now let's come to the gradient, which is the bedrock or the main principle behind um, doing gradient descent and all sorts of operations that you day to day see in machine learning or deep learning or whatever. So one of the major uh, notations that you use often is something called gradient. Now, what is a gradient? Uh, as high school students, we might have learned about differentiation, which means that you want to find out slope of a curve. And gradient is just uh, extension of the same notion. So for example, gradient is generally written as this delta sign. And when this delta sign is taken over a function, so your z is actually a column vector. So when you start with a column vector, which belongs to, for example, I don't know, maybe m-dimensional object, a vector, and then this is equivalent to partial differentiation of the function with respect to all elements of the vector, which means that if you have an m-dimensional variable, then you just differentiate them with respect to individual variables of that vector. And what you get is actually a row vector. So this is a row vector, and we started from a column vector. So we have converted a column vector to a row vector. So this is actually interesting to remember, or important to remember, that Z is a column vector and delta gradient of G is actually a row vector. And the conversion is happening when I am applying this delta Z with GZ. Now, this is actually a a simpler version of presenting this gradient. Now, as we have already seen that there are functions which can actually convert a vector to another vector, such as this operation. Therefore, there is also an associated gradient operation that operates on such functions. Now, before going into that particular function or going into that differentiation or gradient calculation for such a function which takes a vector and gives us back a vector, we'd first understand that what we are doing here actually. So h is a function which can take an m-dimensional vector. Let's assume that n is less than m for this case. So, and produces an n-dimensional vector. Therefore, you can think about writing h as, again, we can assume a column vector, a vector of functions. So these are vector of functions where each of them is actually a real valued function that maps an n-dimensional object to a real value. And how many such vector to real function that we would need to make it an n-dimensional object? N functions. So we can write this h function, which is supposedly a complex function that takes, well, I should not use complex, I mean complicated function, and because I'm talking about real, so complex might have other meaning, not to confuse someone. So we are still in the real domain. We are not talking about anything beyond real numbers. So just concentrate on the function h, which is real valued function, which could be written as this, parts of disjunction where each of the variable of such a vector is actually a function. Now, each of those functions can take a real number and can convert it to a real value, which is an amazing thing. Now, this will help us actually to understand that how to calculate the differentiation of such a function. And we will see how that might happen. So you have now a function which can be written as this, parts which are making this a column vector. When we take gradient with respect to the z, which is again a vector, and this is actually the crux of this problem here, or complicatedness, that we are now differentiating with respect to a vector throughout this discussion. So we are very familiar actually with about differentiation with respect to variable, but we are not quite familiar with this differentiation or taking gradient with respect to a vector, which is something to be inspected closely. So when you take this gradient z with respect to hz, what you get is not actually, a vector, but a matrix. So this is kind of a way of converting an m-dimensional object to an n-dimensional object or vector. So how do we do it? Remember, this h1z is actually a column vector which can take a m-dimensional object and convert that into an n-dimensional object. So z here belong to a real valued m vector. Now, one can think about writing this as differentiating this function again and again with respect to all these m variables, and keep on doing that for another function and another function and so on, and for actually all functions, and there are hn such functions. So we can think about writing this, and this will become So this is n cross m dimensional object. And this is understandable actually. What it means that whatever that object is, generally known as Jacobian actually, it is an n cross m dimensional object. When you apply a m dimensional object, which is say m cross 1, if you take transpose of it, it gives you an n dimensional object or vector that you want to get at the end of the day. So just to recapitulate, you can actually, write this thing down as different such versions of m to r, rn to r, or vector valued function. So you can imagine this h1 as something which is this kind of function like g. So it's kind of a concatenation of such things, actually. So in other words, one can think about writing this as a column of multiple differentiation or differential or gradient of, so let me use the gradient term just to make it easy for us. So this is, okay, there is this funky line here. And then we would have, oh, should make it correct. And I'm so sorry. So we would have this h2 and so on. And we have n functions. So we have hn. So this is again a gradient function. Now there is one little thing I want to make it clear before going ahead. That is, there is this interplay between transpose and a vector, and it is probably interesting enough to mention because this might be differently expressed in different books, and that can lead to confusion. So Z, we have assumed, is a column vector. So Z is termed as this. Now one can think about also differentiating or taking a gradient with respect to Z transpose. And that actually doesn't change anything except uh, making the answer a column vector. So if you differentiate or take a gradient, maybe I should write, I should write take a gradient rather than differentiate. Take a gradient with respect to column vector gives you a row vector. And taking a gradient with respect to a row vector, so a column vector is Z, a row vector is Z transpose, gives you a column vector. So that's the only difference there exists. And rest of the things are quite similar. So you can actually, interchange between them. So taking a gradient with respect to Z transpose is nothing but taking a gradient with respect to Z and taking a transpose of this, because those are basically the same thing, as you have seen. So this notational, assumption, or this notational uh, uh, sort of uh, this notational, I should not say dogma, but rule, maybe you can say, is used in different books. So maybe it makes sense to use this rule and use it throughout our discussion. So this is a convention, so to say. So we have like a few conventions that we made. One is that Z is a vector. It's an m cross 1 column vector. When you do del G del Z, which is written as this, then you get a row vector, which is 1 cross m. And this has same dimension as Z transpose. So Z is M cross 1, so Z transpose is 1 cross M. So this is just a common knowledge. Now, how this can be used in different problems in real life. So one of the well-used and well-formulated example of, or not example, or overused metric that we use in machine learning is actually the dot product between two vectors. So a dot product between two vectors. So what does that mean? It means that it, takes, say, Z, which is again an M cross 1 vector, which means that you have Z1 and then Zm, something like that. And a function can actually produce a real number if you take the norm of it. Now, this norm operation can be written as Z transpose Z. Now, what is Z? Z is again an m-dimensional object. So Z transpose is an 1 cross m-dimensional object. C is an m cross 1 dimensional object. So Z transpose Z belongs to a real, it's a scalar value. So you can say that G of Z is a function that maps m dimensional vector to a real number, which is exactly what we want. So we established that GZ, which is actually this, which is actually Z transpose Z, is a real valued function that takes a vector and make a real number out of it. Now, what's the gradient of such a function? So you might ask that what is this? Now, this is a very well-formed question, and now we should be able to answer this. From the formula, we know that if Z is a column vector, then we get del G Z1 and del G Z2, del G Z2, and so on, okay, del Z M. Now, what is GZ in terms of Z1, Z2, Z3? It's actually a multiplication of two vectors, or a dot product between two vectors. What is a dot product between two vectors? We know it's expected that we know that this is nothing but, if you don't know, that's fine. It's very simple. You just do an element-wise product between itself and the vector itself and its transpose. So it's Z1 square plus Z2 square and so on. You can write this as Zi square or something like that. So when you do this gradient of G, what you get from here? You get this row vector where each of the quantity actually become like this. Why is that? Because in the summation Zi square for I equal to 1 to m, all the quantity except what is being differentiated with is constant with respect to that, because it's a partial derivative. So if you take, for example, del Z1 with respect to all these quantities, rest of this becomes 0, and this becomes 2Z1. So you get something as, this. So now you can, of course, write this down in different ways. One of the ways you can write this down as 2Z transpose. So this is actually the form that you get when you take the gradient of G with respect to C. And there are many famous functions that you can take as a challenge and work it out if you want to. For example, one such function is this, where of course C is again a real vector, and C is actually a term which is m cross m. And therefore, when you do this multiplication, it actually gives you a scalar value, a real value, because Z is M cross 1, and you take the transpose, you do M cross M, and you do, M cross 1. So you basically end up with 1 cross 1, which is a real number. Now, you can also write down what it means to do this operation. This operation basically is a giant sum of things. So you have this Zm, you have your elements here, you have the vector again here, and when you take a sum, what you do is that you first do a 1 cross m versus m cross m. So what you get is a 1 cross m value here, and 1 cross m is just a multiplication between these quantities and these quantities, and so on. So you do this, and then step by step, what you get is, first you get this giant summation between the values of C1. Maybe I can write a J here, and then you get Zj, and J belongs to 1 to M. And you can have this for different values. So the second term here will be what? We can write the second term as maybe in red, just to differentiate. So this term should be here. I'm writing it here for lack of space. And you get J equal to 1 to M, C2, J, Zj, and so on. So you have such M terms. You have a second multiplication here. What does it do? Now this will multiply Ci, C1j, Zj, this into Z1, and then plus you have C2j, Zj, Z2, and so on. So in some sense, you are actually multiplying all possible quantities that you want to multiply. So if I make now the variable 1 as, this and this as I, this also will have a term. So also have a variable, which means that C goes from 1 to M. Sorry, oops, I think I lost my multiplicity. Oops, what did I do? Okay, how can I remove this? Okay, this is fine now. Sorry about that. So maybe I should come back to the old thing. So this becomes I1 to M, and this becomes J1 to M. And then what we get here is Cij, Zi, and Zj. So this whole summation is actually what we call G of C. Again, a function that maps a invariable thing to a real number. Now remember, of course, you must be thinking that, okay, C is a matrix here. So why you are writing this input as an in-dimensional vector? That's because C is constant with respect to C. So it's actually not a function of C. Of course, if it were a function of C, we would be talking about a completely different operation. Now, how do solve this? Uh, Actually, it's quite simple if you think about it, because uh, again, we would apply the same principle that we learned in previous pages, which is when we want to differentiate with respect to the whole Z, it becomes a row vector where we differentiate individual term with respect to uh, a variable of the vector. So we have a term here, which is summation I, J, Cij, Zi, Zj. So what if I differentiate with respect to del G, del Zi? Now that's a great question. So what would happen is that we would single out the terms which has Zi in their formulation. So if you unfold this summation, what would happen? One thing would happen is that there will be two kind of terms here. So if I really have to unfold this, there will be such terms where you have I and where we have I and J, and there will be a lot of terms which neither have I, uh, which doesn't have I actually. It can have J, of course. So if we write that down, then you can go back to this term and try to realize what I'm talking about, because there are these terms where a particular Z was there. But nevertheless, so we can write this as something like this: Cii Zi square. So this is like one scalar value. And then we have all the other terms where Zi just come as a multiplier. So we can think about all such sums where Zi happens to occur. And we can take the Zi out of those, and we want to take all such Z's where this is a coefficient. So you get I, J, Zj, and then you have a lot of other terms which have no Zi. So this will have some Zi which you can take out for now, and I will explain why. And you have a lot of terms which does not have any Zi. And now we will differentiate this with respect to Zi. There's a reason why I wrote it in such a way. It would make our differentiation easy, because now we can write this as Zi because this term has Zi. This term, the Zi, will just cancel out in some sense because it becomes 1, and you are left with, for all such J, which is not I, and all this term which didn't have any Zi just becomes 0. So what is the output now? So you have this, uh, 2 Cii, Zi, and you have this term where you have Cij, Ci. Now, one thing that we should remember is that there will be two such terms where this might happen, right? One is Cij and another is Cji, because there are two ways to explain it. So you can actually write this as, maybe I should actually rewrite this equation in such a way. So Ji, Zj, and then we have these terms which will all be zeros. And it's actually very easy to see, and you can see it if you take a small example with three different variables, for example. So you can imagine that you have this 1 1, the C to be 3 cross 3, then you have like different terms like C11, C12, C13, and you have C21, C22, C23, and you have C31, C32, and C33. And when you differentiate this with respect to del Z1, the only things that you'd care about is this part. So we are actually writing those parts. So the Cij and Ci is actually talking about these two things. And Cij and Ci, these two things and these two things. We have singled out this. Now, if C is a symmetric matrix, which means that it has exactly same uh, uh, elements when you take it like the diagonal, all the elements are exactly same, then all these off diagonal elements are actually symmetric to each other, which means basically nothing but Cij equal to Cji. So if you have that, then this becomes even more simpler. Uh, and we would see that because this becomes actually 2 Cij. And so you can actually write this term as 2 Cij, where j not equal to I, and then Zj. Now there is another level of simplification that you can do with it, and if you include this term inside this, you don't actually need this ugly inequality. And what you can write actually is Cij Zi, or actually J, and you can vary your J from 1 to M, because now this actually contains all the terms. The first one is the C11, and there was a 2 behind it because this was the coefficient of Z1 square. And then you have all these other terms which occur twice. Now, this is kind of interesting because what it's telling us is that this summation, excuse me, is just a summation or a product between two quantities, a vector and let me take the 2 out, a vector and a matrix. How is so? So you can think about this as taking this row, which starts from Z1, goes to Zm, and then multiply this with respect to this quantity M1, and so on. So, you can uh, keep on multiplying this. And if you multiply this, what would happen is that you are actually multiplying 1 cross M to M cross 1. And it's easy to see it, but I can also show you how you see it. So if you take this quantity, uh, okay, maybe I should not write this uh, as a matrix notation. What I mean is that you can write this as this. So I was differentiating with respect to Zi. So maybe I should write I here. Yes, I think I butchered the notations a bit, but maybe I can rescue it. So this to mi. So what is happening here is that you are multiplying the mth column with this. So sorry, the ith column, okay, ith column with this. So when you take a gradient with respect to I, what you are basically doing. So if you unfold this quantity, what is this quantity? This quantity tells us that you do Ci1 Z1, then Ci2 Z2, and so on until CIM ZM, basically this. And if you look at this sum, this exactly tells you the same thing. So in some sense, this is Z transpose, and then this matrix, but not the entire matrix, but the column, the mth column of the matrix, sorry, the ith column of the matrix, is something like this. Okay. So this is the whole idea of taking the gradient, and you get such results. And you can actually uh, take as many functions as you want and try to see that how uh, these functions are uh, uh, interesting. So for example, if C is not a symmetric matrix, which means that if C is any matrix, so for example, you have this, then if you take a gradient of this gives you, you know, this quantity. And it's kind of easy to prove because you can come back here and you see that if it's not symmetric, you cannot take the sum. So you have to write it differently. One is C transpose and C. So Cij is not equal to Cji. If this happens, then it will have different values. So this is all for today. We would start with Hessian in the next discussion, and it would be more interesting, I suppose. Hope you liked it. See you.